Well, I'm sure everyone on this call knows this, but the idea quantum computing, it's literally what it is. So what it's not a brand name, it's not a buzzword. What quantum computing is it's taking advantage of quantum effects to make calculations. And nobody really understands what happens in the quantum world is very non-intuitive. So even the best quantum physicists in the world will readily say, I have no idea how quantum physics works. And so any intelligent person who's not a quantum physicist, you should be very comfortable mirroring that and saying, I also don't really understand how this works. It kind of gets at the fundamentals of the structure of the universe, and it can get into things like parallel universes and all these wacky things, but we're not going to go that far. But the fundamental thing that you're thinking about when you're thinking about quantum computing is, how do we take advantage of the weird, spooky behavior of subatomic particles, and how do we use that for information theory? I guess the last piece I'll just say, these were first theorized. I'm sorry, Marco. These were
go ahead.
Yeah, these were first theorized in about 1980. So it was in 1980 that the first individual was like, oh, you know what? I bet you could use this for computing. And then the first algorithms were kind of developed in the 80s as well, saying if we had a computer, we could break encryption. And here's the algorithm that we could actually use to do it. And it wasn't really until the 90s and the early 2000s that people started actually building hardware that seemed to work. And then it wasn't again until the 20 teens, and this was early, this was much faster than most forecasts, that people started building computers that they thought they could do some significant research with, or maybe even start to build a commercial industry around. So commercial industry has really emerged since since around 2011, 2012. And it's picked up a lot of steam and has a lot of investment and a lot of momentum now, both on the commercial and the government side. So that's the background.
Yeah, so that's a great summary. In fact, I think the easiest, and I'm just maybe again going to show a couple of slides to sort of repeat the concept that Paul had explained. I will not try to explain what a qubit is and superposition, all of that. And some of you might have seen slides, and actually some of you might be in the field. I think that doesn't really tell the story as to why quantum computers have a greater computational power. The truth is, as Paul said, there are the laws of physics at the microscopic scale are different from those at the macroscopic scale, so at our scale. And that difference is what we try to exploit by controlling a system at the microscopic level to do things that we are limited in because of simply how things work at our scale. And typically, one way to consider what quantum computing as a technology is useful for is starting from high performance computing. And that is because quantum computing ultimately is supposed to be used for difficult computational problems. It's, we've come a long way in a few decades from like the initial rudimentary computers to what we have now. I actually had this slide of, I think I created this slide in May, and I've realized while I was sort of reviewing it that in May, this was IBM Summit was the fastest computer in the world. And only in a couple of months, it is no longer the fastest computer. There's one now in Japan, which makes this machine that you see here in the picture the second fastest right now. So you have impressive specs and performances. There are reasons, though, for which we believe that we are not going to be able to continue to make progress as we've done in the last decades and do exponentially better with these machines in the future. Regardless, even if we were able to continue progress, there are problems, and as Paul said, that are difficult. And in particular, any problem that has to do with a description of a microscopic system, we believe that is difficult on a classical system, and pretty much no matter how big your classical system is. And this is the idea that Paul was referring to, in fact, from the early 80s. So why don't we think about then using a microscopic system, controlling it to then describe another microscopic system. So this is the idea behind quantum computers and the fact that it really is a quantum. It refers to quantum mechanics that describes these microscopic systems. It turned out that the sort of operations that we could do, at least in principle, on a quantum computer, they would have been helpful to describe microscopic systems. But actually, not only that, there are some other computational problems completely unrelated, for which the same techniques would have actually led to a result that classically, with classical methods, would have been fundamentally possible, at least for the algorithms that we know now. And so the classical example is Shor's algorithm from 1994. This is probably one of the most famous algorithms in quantum computing, which allows the factorization of a composite number in its two primes. Its relevancy is that the technique of actually, so the difficulty around factorization of a composite number is the principle behind most of today's encryption. And so it is being able to find factors efficiently is a problem that has, the great relevance, just beyond the mathematical interest. There are, of course, many more algorithms, and there are categories and of fundamental mathematical ones and actually more practical ones that have been developed. And I think the effort on algorithms has been as intense over the last years as the hardware effort. Now, the last thing I'm going to show, because I suppose often we talk about quantum computers, and there's that leaves a doubt as to what these machines look like. So I've got a picture of some Rigetti's computers, which is this, so Rigetti, the company I currently work for, manufactures the components that go in quantum computer, assembles quantum computers, and offers them on the software stack, and offers access through the cloud. So a quantum computer is fundamentally one of these white cylinders with some control, so all the electronics that you see outside. So these are about 1.5 or so meters high, and this is our facility where we're hosting them in Berkeley. Now, I've been talking about a microscopic system, and this thing looks anything but microscopic. Now, so another picture that sort of shows what the quantum computer is, that's something that shows what's inside the cylinder. And inside the cylinder, it sort of looks like this. And I won't spend too long, of course, talking about what's all of this stuff. This is fundamentally, in summary, what controls the microscopic system that is the quantum computer, which is this inside this little golden disk in the bottom. That all the rest is control systems, and actually the chip is within that golden disk that you see here on the right. That is really the core of the quantum computer. So it's a very small system, as you would have expected, but of course the control system isn't that small. This is only one way of building quantum computers. It's the superconductive approach to quantum computing. That's the one we use. That's the one that IBM is using. That's the one that Google is using. This is far from being the only possibility. There's intense research on many other possibilities. They're listed here: trap ions, photonics, etc. And I'm only mentioning 2 of the players involved in the hardware effort. This is far from being a complete list. It's a much longer list, even just at the hardware level. The last thing I would say is, I think as a business user now, the natural question is, how do I program the stuff that's in the cylinder? Now, it is easier, fortunately, than you might think, because there is, and this is again our software stack, there are equivalent software stacks, but what actually is given to the end user is development environments accessible to the clouds that are pretty much very similar to what you would be using for classical computing. The thing that isn't similar, and I think that this is an important point to stress, is the fact that quantum algorithms are very different in nature, and even if the programming environment is similar, for someone to be able to write a quantum algorithm, there is, of course, a bit of learning and significant differences that need to be understood. And even understanding the applicability on a business problem isn't trivial, just because, again, the logic of these algorithms is profoundly different. So the effort on hardware has been significant, has been great progress, but equally, I would say that the effort on algorithms and applications in the working, in fact, with businesses and in trying to understand what the applications are, it's been equally important. And I think on this aspect, this is how QBranch, so on the algorithms and application with business users, this is how, at the center of QBranch proposition. And maybe I'll let Paul talk a bit about how, in fact, the project started and how it developed over the years.
Yeah, that's right. I wonder if we can skip ahead just real quick, Marco.
Sure.
And I will make a comment and then you can correct it or add to it a little bit, because I think at this point we should talk about what are the types of problems that quantum computers are good to solve just from a formal perspective. And I haven't been at Rigetti QBranch in about 2 years, so I'm a little bit rusty on this. But what we were looking for when we were working with a number of organizations are classes of problems that take advantage of quantum behaviors that allow us to interrogate a massive number of incredibly complex and intertwined numbers at once. So one of the classic examples of a problem that you can address very well, not necessarily solve with a quantum computer, is something like a traveling salesman problem or a combinatorial optimization problem. There's many classes of problems where you need to evaluate what's the best combination of a large number or even a small number of variables. And in those cases, there's some algorithms that you can use to create some shortcuts. But for the most part, there's no mathematically efficient way to solve those problems except by brute force. And the law of exponents means that some very practical day-to-day problems can become intractable incredibly quickly. And so, the traveling salesman, I'm sure those of you that have any computer science would be very familiar with this. Those of you that don't might find this a little bit interesting, or maybe you've learned it in another way. It's a common problem. But if I have 50 packages to deliver around London, finding the quickest route to do that is essentially, actually usually get this wrong. It's like n to the 50, right? Marco, please correct that. Is it?
Yeah, it's exponential in the nodes or in the cities or in the stops.
Yeah, but it's not n to the 50. It's like 2n to the 50 or something like that.
Yeah, well, I think the 50 appears as the exponent, so it would be.
That's right. So if you have 50 nodes, it's an exponent of 50 to basically, which means that if you add one more stop, you've now made the problem an order of magnitude more difficult. So it will take 10 times longer to run that problem. And something like 50 or 100 packages to deliver, that is a very, very practical problem. And you can run into these types of problems all the time in any type of AI environment where you're looking at a system that has 50 variables is not a lot of variables for an AI system. We regularly look at those in the thousands. And so being able to look at what are all the combinations of behaviors between all those variables, that's a problem that with even the most powerful computers, the amount of time it would take to solve that efficiently is in the billions of years. And so you can kind of run into these problems all the time. So what we were looking for, those types of combinatorial optimization problems. We're also looking at, there's another class of problems that's gonna skip my mind. So I'll come back to that. But basically say that what you're looking for is not necessarily problems that are really big or sort of seem very complex. They can often be very practical and very day-to-day. But what quantum computing allows you to do is it allows you to unlock all of those different combinations very, very quickly. And it does it by simulating that as a physical energy system rather than as a series of numbers, and then finding energy states that correspond to optimum values there. So it's more like finding the lowest point in a valley than it is like first calculating every point in that valley and then comparing those numbers. So it can be a very efficient way to solve certain types of problems.